Alrighty, who's ready? Last talk of the day, huh? Now, I should just thank my collaborators before I start. One of them is Victor Solo, Du Bois-Bowman, Daniel Drake, Goran Marjanovic. I think that'll cover enough people to share the blame for what we're about to say. So, I'm going to start an argument, right? It's the end of the day. We can do this. You see, we're talking about connectivity, and I just could not care less about nodes and links, right? Yeah, Gail's sort of shaking his head already. Nodes and links, edges, vertices. It's the last thing I care about, right? Because let's think about, we're sort of 20 years, 25 years into neuroimaging, and what have we changed since then? Right, looking forward. So we started out looking at just voxels, individual voxels. These days, when you're looking at voxel-wise analyses, like through pattern analysis and things, you don't specify just a single voxel that you're interested in, right? You're looking at distributed patterns across the brain, right, from a voxel-wise typical point of view. The same argument applies in connectivity, right? 20 years from now, the last thing we will care about is the individual nodes and links, right? You can imagine the data's going to get better. Our methods will get better, right? We're going to have such dense, sort of large networks to deal with, right? This little link over here or that little node over there, it's not really what you care about. You care about some idea of the underlying shape beneath and sort of like supporting the whole brain activity, right? And so you can think about this in terms of, we sort of start at the local features, nodes, links, clusters, then you get through this unknown territory so far, through these mesoscopic or mid-level distributed features, right? Until you get up to, at the other end, these global features, which are just a single number summary at the end, right? So at each end, it's not quite so useful. In the middle, it's really rich, collection of things that we can do, right? And topological data analysis is this emerging framework. It's sort of like this pure and applied math field of topology meets statistics, and see what we can do with that. So our motivations are really sort of about looking at consistency and stability. Can we make consistent conclusions when observing across scales? Right? That's a real fundamental thing that functional connectivity has struggled with for upwards of a decade now, right? If we take two different parcellations of exactly the same underlying data set, can we make exactly the same conclusions about the shape in there, right? Inference, right? This huge problem, once again, of selecting an appropriate link strength threshold in a weighted functional network. TDA, or topological data analysis, is exactly the right tool for the job to escape from that problem. Signal-to-noise ratio. Can we separate interesting from non-interesting patterns? Right? This idea of feature engineering for then predicting from. But can we extract principled, sort of these unsupervised features from networks, separating, once again, basic and complicated patterns? And this idea of, we've talked about a whole lot of different concepts today in and around community detection, modularity, clustering, right? And sort of a few of the speakers have talked about this idea that we need to generalize beyond this to allow perhaps overlapping or disparate clusters or features to exist, right? And topology it can handle that, right? But underlying this is this whole basic science problem of finding the shape of brain activity, right? That's what we're really interested in. And so we're going to talk about persistent homology here as one framework under this umbrella. There's other methods such as this mapper algorithm. If you've ever used ASD software, that's what they're doing. Related areas such as graph signal processing, that's related to homology, clustering, geometry, all these sort of other fields have very specific and formal tie-ins to what we're talking about today. But this is a sort of an area on its own. So topology, right? The word gets thrown around in network analysis quite a lot, a bit lazily perhaps. There is a real formal field of topology in mathematics, right? It's the study of shape properties that are preserved under continuous deformations. Another way to describe that is qualitative features, right? So this, we're talking about persistent homology. We'll get straight into this idea of homology, which is the study of loops or holes in things, right? Of various increasing complexity of holes, right? So you can have like 0-degree holes or 0-dimensional holes are just connected components, clusters. 1-dimensional holes are loops. 2-dimensional holes are voids. We're going to have a bit of a chat about examples of this, but another way to describe it is sort of just donuts and coffee mugs, right? That's the classic topologist joke is we can't tell the difference, right? So on the left there we have a donut, and on the right we have a coffee mug. I mean, the great irony of the American donut industry is that they make all their money off coffee, selling coffee, right? But the point I wanted to make, in a real simplistic sense just for now, is that the donut and coffee mug are indistinguishable, but our donut coffee mug that we've just added in is different, right? We can tell the difference there because it's got an extra hole, right? Now, we're going to sort of tackle this from a pretty basic idea of like looking at holes. So really what we're getting at is if we throw away any idea of distances, what do we have left? Right? That's the idea of a qualitative feature, right? The underlying shape that cannot be trivialized to a sort of arbitrarily small part of our shape. And here we have like a torus that is a torus no matter which way we look at it, or a donut. And it's pretty unambiguous, even though we have a different sampling. Right? We have a different, say, average path length between all of our nodes, right? But we don't care about our average path length for the sake of looking at the shape of that thing. Right? So, but if we try to motivate this from a typical network point of view of nodes and links, like vertices, edges, faces, right? We can do this, right? And we can calculate things that are invariant to the sampling, right? So an answer, so we demanded from the start, we wanted an answer that stayed the same no matter how we sampled our network, right? So here's our circle of brain activity, right? It's fairly simple how we're going to start out, right? And if we sample it with only 4 vertices, 6 vertices, sorry, 8, 6, 20 or 12, there's 5 basic shapes. If you take the number of vertices minus the number of edges, add the number of faces, you get this invariant, right, called the Euler characteristic. Now this is just an example of a topological summary, right? But it was nice that we got the same answer every single time, no matter how we subsampled our, admittedly very simple brain activity, right? In terms of these, and we can call these 0, 1, and 2 simplices, right, in a sort of a topological language. But the point there was that we could get the same answer. Now, let's go one better, right? Because we actually had different numbers of vertices and different numbers of edges. Well, if we change this word up the top from sampling to invariants themselves, right, we can construct that same Euler characteristic invariant out of component invariants, right? So now we're back to our idea of homology, looking at holes and loops, right? And so we get these Betty numbers, which is just the number of these features. So Betty 0 is the number of connected components. Betty 1, the number of simple loops. Betty 2, the number of voids, right? And if we do the same style calculation nicely enough, right, add up the number of connected components, and all these examples down the bottom, we have one connected component, right? We have one object. Let's say, look at the torus, right? The second one along. So we had Betty 0 equals 1, Betty 1 equals 2, right? There's 2 loops in it, one that goes around and one that sort of goes over the donut, and there's 1 void. And the simple, with apologies to a few topologists, this is the easy way to calculate these numbers, right? So start from the right, you've got a drill that, how many holes do you need to drill to pop all the voids, right? Just 1. I mean, it's easier for the double torus here, right? 1 void. How many scissor cuts do we need to make to get rid of all the loops? Well, there's 4 loops to cut open, right? 2 in each side. And of course, our count von count, all we do is count the number of clusters. Well, we've got 1, right? And so you can see down the bottom now, as we get increasingly more complicated topological shapes, we get a different Euler characteristic that was sort of summarizing the whole shape, right? Now, obviously, that's only one number. It's not a rich description like I was promising you at the start. I said we're going to be able to do a whole lot, and we've done something kind of simple And we've shown some sort of invariance to sampling, which is good for a start, but we haven't really solved the whole problem, which is this classic old problem with which link strength threshold should we pick, right? So now we're in our familiar domain of networks, right? We've got the same network down the bottom. We've just, on the left-hand side, we've left some of the links in, and on the right-hand side, we've sort of judiciously chopped them out. And we can see on the right, we've got more of a hole than we had on the left, right? So it's obvious that some holes are more important than others, right? If we have a big hole, it's sort of a big feature. It's a strong feature, right? If we have a small hole, it might have just been due to noise. Can we deal with that? Well, this is where this word persistence comes in, right? Persistent homology. What was the persistent feature, or the persistent features over a range of thresholds? So this is sort of Rob Grosh, he's a topologist, excellent topologist, and he has probably unwittingly donated this picture to almost every topology talk ever. It's just a really nice one, and I couldn't come up with a better one myself. So here's this underlying donut shape, underlying 2D torus, and that we've taken a point cloud of samples from it, right? And as we gradually expand a radius threshold, so this is sort of like our link strength threshold, as our radii intersect each other, we join up the associated nodes and links. And you can see as we join up 3 of them, or 4 of them, or 5 of them, however, we get, let's say, like a 2-simplex, or a 3-simplex, or a 4-simplex, which is just more and more like the cliques, right, with the more and more nodes all connected together. And what this lets you see is we can observe, first of all, we did put this slide in, right? So we can observe the formation of holes, right? From on the left-hand side, there's no hole. In the middle, there's a hole. Right-hand side, it's been filled in. Right? As we gradually expanded the radii or the threshold, right? So holes can be born and then they can die. And we're going to keep track of how long over our threshold range they stayed alive. And that's sort of an indication of topological features, right? So what can we do with all this, right? So we're still back on our toy example here, right? Well, we said before we have these homology. You can talk a lot of topological language, but we've got to at least say the word homology, which is these loops of different dimensions, right? So H0 is just connected components, right? How many individual pieces do we have? H1 was simple loops. H2 are voids within a sphere, you can think, right? And this is called a barcode representation of that progression, right, over that filtration of our weighted network. And each of those lines down the bottom is sort of tracking the existence, right, the birth until the death of each of those features, right? So let's just, zoom in on one of them. Let's take this one as an example here, right? So we've got sort of, how many? 1, 2, 3, 4, 5, 6, is that 6 clusters, right? And sort of an individual node by itself is still a cluster, right, or a connected component. We have 2 loops, right? So 2 of our H1 homology bars, right? And none of our H2 ones yet. So we don't have any voids yet. But then later on, we get a void just quickly, sort of, it's up in there, before that in itself gets filled in as well, right? But what we're seeing here is, and you can obviously go to higher and higher and higher degrees that characterize more and more complicated aspects of your network, but we've got a really principled, unsupervised, a sort of rigorous way of decomposing the entire shape of a really complicated network in a mathematically, sort of a comprehensive way and really organized way. Computationally, we may not be able to access all the really complicated parts, but theoretically, we've at least done a good job. Turns out, computationally, it's not so much a problem because most of the interesting stuff is in the simpler shapes, right? So we're going to have a couple of examples just to finish off. From Human Connectome Project resting state data, we're going to have 3 examples, just very quickly looking at the architecture. Now, and everyone's using this word dynamics here differently today. Not to make too much of a point of that, but here we're going to use it to represent as a proxy for link strength, right? And the importance of acknowledging link strength over just the architecture, just the presence of particular links, right? Consistency between parcellations. Right? I promised you I would show you that topology is a good framework for that, and the persistent homology of sparse networks, right? So we've talked in and around all of these issues through a lot of the other talks today. I guess we're not trying to do any real science as such here today, right? So in this talk, it's about healthy subjects, but we're really trying to set the scene and provide the justification that topology is an appropriate tool for the future, right? In a sort of essentially a validation that it does what it said on the box, right? So this H0 barcode, just looking at the connected components, right? It's actually the single linkage clustering, right? Funnily enough, in a nice happenstance, it matches up with your minimum spanning tree of your network. As you build up those clusters, it joins up the minimum spanning tree, right? And we can draw all our bars of our H0 barcode. This is just for a single network, right? And being in a stats department these days, all I want to do when I see those points is I want to fit a curve, right? It's a sort of an instinct that I want to do. And then let's take an example. Which one's first? This one's first, right? So if we fitted a curve for a single representative network, and this is H0, looking at the real basic shape of a network. We're trying to show some consistency between people, right? And we can sort of look at the difference between all these curves over a collection of people, right? So just as a slight sidetrack, right? And so the difference between this idea of architecture and dynamics. So along the top row, now this is probably the first really controversial thing I'll say. We'll go from the right, top row, correlation. This is a map of the repeatability of correlation network links, right? Assuming we had put a single threshold on, just for argument's sake here, right? The probability, the chance of finding each individual link across the network over hundreds and hundreds of correlation networks. Well, it turns out correlation gives you a different answer every time. Almost, every link has around about, a distribution around a 50% chance of being detected every time, which is a bit uncomfortable. Gail made quite an important point about how conditional independence, right? So not the marginal correlations like this, but a partial correlation might do better. And we see that, right? If we move over to the partial correlation, we've suddenly got these links being somewhat reliably found. And this is a map of the repeatability, not just of the link strength, but the repeatability of finding different links, right? And then as you go to a sparse partial correlation, as Gail had in some of his better results, right, we get an even, this is a qualitative view on it, but we get a better, richer view of the full network. And then this DISCO method, this is something we came up with over the last couple of years that sort of extends sparse partial correlation to also account for the temporal dynamics or the autocorrelations within fMRI data as well. And you get, yet again, a slightly richer and perhaps more interestingly repeatable network thereafter. But the second row is where this is kind of key, right? Because now if we just look at the minimum spanning tree architecture, right, just the existence of those particular links and the repeatability of those over hundreds and hundreds of people, every single one of these methods did around about the same, right? What's going on? And more to the point, this shape down the bottom, if you read the network node labels, you find that this pattern pretty much matches up with what we generally call the default mode network, right? Now this is a bit worrying. This is a little bit controversial perhaps, but it's quite worrying. First of all, finding the default mode network ain't that special, right? More to the point, if you can't find the default mode network in whichever method you use, you've really stuffed up, right? Because we found it even in these pretty messy correlation networks, right? But perhaps there's not that much in there. Is there? Well, let's see. Right. So if we suddenly bring back our idea of the dynamics into this whole story, right, and look at these H0 barcode curves, right? It's sort of like my point here is that just the architecture did not tell us or explain why the full network repeatability was so different. Whereas if we look at the dynamics right? And I mean, we might need to zoom in on another day, but you get more and more and more consistent curves, right, for these curves representing the really basic architecture, basic topology of the network, as we get a more and more rigorous network construction method, right? So the take-home message there is don't use correlation, right? Second thing we're going to do, we go back to our single individual curve there, and we're going to take the derivative of that curve. Why do we take the derivative? Because then we can look at the rate of connecting up the network, right? The rate of change. And so here we have the same sort of repeatability maps between two different parcellations. We have 4 separate data sets, right, that we'll show examples from. And those network sort of topology derivative curves between two parcellations, two free surfer parcellations, 87 and 167 nodes, incredibly repeatable measure of topology between the parcellations. However, it's different for every person, right? So each person is incredibly internally consistent if we do this properly. And you can use this as a validation mechanism to tell yourself that, hey, you know, if you show the correlation versions of these curves, it didn't do so well, right? They're not consistent between parcellations then, right? So it's like a sanity check. Now let's sort of finish off with this last example, looking at, so we looked at a few examples just there of the H0, right, the zero-dimensional basic homology. We can look at the H1, which is the simple loops, remember. H2 was the voids. H3, well, it gets a bit harder to visualize it, but you know, we're getting more and more complicated representations of it. Now, I mean, on the left I've got this network repeatability map, but this is the decomposition of just a single network. And you can see just how much detail there is in that network, right? We're going to take a look at just the final slide here on the H1 repeatability over now 400 of these, right? If we take 400 of those maps up the top right, do a histogram of the average bar length, right? So longer bars were sort of stronger features, right? Which will be on the right-hand side of each of these plots. Smaller bars will be on the left-hand side, right? So you're broadly corresponding to stronger and weaker features. And then this blue bar is saying, well, on average, we had one of those features in every network. If we go all the way over to correlation, well, there's this funny story coming up again. That's correlation networks, on average, and very consistently, right? So we've got error bars around this, 95% confidence intervals on the mean. Correlation networks very consistently have almost no topology, right? If you're ever thinking about using correlation, simple linear Pearson correlation to do functional connectivity, you've thrown away almost all the information in your data, right? Except for maybe that default modes network structure that we saw popping up before. But this shows fairly unambiguously correlation does not really do the job you wanted it to do, right? This L1 sparse partial correlations that Gal was telling us about, wow, we get a lot more structure. Good on us, right? And we're doing pretty well. Same as if we do like a dense version of the same, but in a time series fashion. I haven't really labeled the methods here, but the real surprise comes in, right? So Gale encountered a few problems when he was using his, when L1 is sort of like an approximation to this idea of sparsity. But truly what you want is a different measure of sparsity called L0. Now's not the time and place to harp on about the differences, but that's like the L0 is sort of like the ideal version. And if we suddenly come up with a method to calculate the ideal sparse network connections, then we see this distribution into strong and weak topology, right? So we've actually separated our topology into a bivariate distribution there, which is probably the first time it's been shown, I think. So I'll finish there. There's a reading list that you can look at. Of particular note, I would recommend Chad Justy's website up there. Fantastic reference. He's got a whole lot of papers. And then there's a couple of posters in and around this theme across the conference. So I'll stop there.
Okay. So we're going to move straight into question time. We've got about 10 minutes worth of that. You'll have to get up to a microphone to ask your question. The other thing is I'm going to attempt to distribute the questions across the speakers. So once we get a question for speaker A, I'm going to give a preference to a question for speaker B and so on. At least that's the idea. We'll see what happens. Okay, while I'm waiting for somebody to gather the courage to come up and ask, and by the way, this is an educational workshop, so you are entitled, even expected to ask, shall we call them dumb questions, because we need some stuff to be clarified. You've had an enormous amount of material shoved down your throat this afternoon, far too much to grasp completely. I will make a couple of attempts in the last minute to summarise a couple of things for you, but great, we've got a question.
Great talks, all of you, very enlightening. I was wondering if Steve in particular could talk about his views on whether there may be dynamics that are possible to pick up in fMRI without having to rely on on correlation windows. I mean, the things that like the kind of clustering of you talked about the clustering of the volumes, but maybe something like the hierarchical model that Mark showed. Do you think that just fundamentally the model, the states are not there, or?
I think the states are not there.
Thank you.
Yeah, you want to elaborate on that?
Yeah. Here. So I tried to be specific about what I was saying, which is the large-scale correlation structure, because that's where a lot of the claims are that there's clear non-stationarity. We don't see it in our data. Now, if you're asking, could you look at a single connection and make some judgment about somebody's state? Maybe you could. But you saw the variability of a single connection, right? And that's over a relatively large time scale. So it's hard to imagine what sort of signature that you want to see to be able to understand the state. There may be some place in the middle in there where you could find something. So this is skeptical day, right? So I'm skeptical. I'd actually like to be proven wrong, but we spent, once we saw where I showed the matrix of everything changing so much, okay, now we know that it's there. How do we go about showing it? And every way we tried to get an objective way to show it, we kept running into walls. And so it may be the fact that we're using correlation, but whatever, it just does not seem to be there.
Okay, you boys.
I have a question. Is this on? I have a question for Sean Simpson. So I, like Victor, really admire how your approach kind of brings a statistical modeling framework to graph theory metrics. When I think about statistical modeling, I view it as part art, part science. And so in that regard, as I think about the ergo model, let's say, it's not so intuitive to me how to go about even selecting the metrics to involve in the model. And without that intuition, the only thing I would know to do is throw everything in there and sort of see what's important. And so I just wanted to hear your comments or remarks and the degree to which that might even pose challenges as the number of metrics and covariates grows relative to the sample size.
Right. I mean, I think that's a really good point that I didn't discuss as much in my actual talk, is that it is sort of part art and part science, and you do have to sort of artfully choose those covariates. I mean, what informed our decision was basically metrics that have been shown to be important in brain networks, because there are a number of sort of network feature systemic properties that can emerge from networks, and some may be more relevant to certain types of network, like some may be more relevant to social networks, some more to technological networks. And so we sort of started with those that we thought were important for brain networks based on the literature thus far. And we also included some others just to see how things played out. But it's also a good point, too, that you can't just throw everything, can't throw the kitchen sink in there because the model won't fit. So you do have to we took somewhat of a backward selection approach where we started with the most we thought the model could handle and sort of worked backwards, removing those that didn't prove to be useful in the model fit. If that makes sense.
Actually, let me add a comment there. Maybe to think about those features as regressors. So stick in as many as you would like. Sean alluded to the fact that you'll start getting singularity problems, so think of regression with collinearity. Now you need to regularize. So, of course, there's a large number of ways to do it. We've heard some of them today, L1, L0. Nobody happened to mention ridge regression. Danielle alluded to a number of different points. Might be a way to manage this. Remains to be done, of course. Okay. Any more questions? Yeah.
Hi. First of all, thank you very much for the wonderful talks. I have like a general question, like after like integration of these talks. So first, like Dr. Peterson. So you basically showed us the resting state is like stationary. It's not can't be like divided between like different like states. But according to like Dr. Bassett's talk, it seems that like this task data actually can be like have like different like states, which is biologically meaningful. So I'm just wondering, have you also checked about the task data? And if, for example, like if the resting state data is stationary, but task data is not, I'm just wondering what leads to the like the high similarity between task and resting data as shown in Emily's talk.
So I totally believe that task, so if you mix task and rest, you'll see non-stationarity. I showed that. We have some evidence depending on the structure of the task. So think about a Posner task, right? Where you're going to present a cue and the cue is going to reset things for a subsequent stimulus. We have some data that makes it look like that, even on that relatively short time scale, that you can produce a change in state and effectively change the matrix on a very short time scale. It's tough to make this work right, at least in our hands. But so I think you can. I think tasks will do it. If you fall asleep, you're going to change the state. Mm-hmm. So it's not that there's no dynamics to be found. It's that if you're just lying there awake and you're not changing your level of arousal a whole bunch, all those random thoughts. So I left out on my end slides. Here's the interesting thought about this, that your stream of consciousness is a state. It's one state. It's not that there's nothing going on in there. It's just that you're not fundamentally changing the ongoing correlation structure. There's surely stuff going on. It's just not available to resting state fMRI.
And what do you think like leads to like the high similarity between like resting state and task data? Sorry.
And they aren't simple questions either. I don't know. That one's a good I don't know question. So I'll tell you what I believe that the resting state is: constrained by anatomy, but related to coactivation history between the nodes. So as you add a task in, right, that ongoing set of relationships just carries on. It doesn't, the idea that task reconfigures the networks. Well, if you want to call that a reconfiguration, go ahead. But really what it appears is there's this underlying correlation structure on which you lay a small change related to a task.
Okay, yeah, thank you.
Yeah, I just want to give my own sort of thoughts on the possible presence of temporal non-stationarity in resting state. I mean, our experience is very different from Steve's. I think the main reason for that is merely because we don't use a sliding window approach, which is going to have huge problems trying to have enough data to estimate any kind of connectivity matrix. As I said in my talk, when you take a different approach, like the approach that we try and do with a generative model, then you end up with the HCP data, for example, having 100 hours worth of data to estimate any individual connectome when you describe the time-varying activity in the resting state as being made up of 10 states. So this is a huge amount of data, and that just puts you into a completely different situation compared to if you're trying to use sliding window approaches. So my own personal caveat is that if I'm honest, we haven't done the same level of simulations that Steve has done on the sliding window work to definitively show that we can put that one to bed. But we have done some fairly straightforward simulations where we have a fairly straightforward multivariate normal stationary model, and you can show in that context that you don't get the kind of rich temporal structure that we see with the approaches that we use, whereas in sliding windows you would.
So I'd like to say three things about that. One is the HCP data certainly has a ton of artifacts in it of the kinds that I described, which could produce apparent non-stationarity. Number two, the 100 hours, so I was careful to say within a session. The 100 hours, the fact that you could have 10 states lying in there would not surprise me, but it would very much surprise me if it was on the time scale of seconds, and I can't remember the third thing I was going to say. At least if Tom Yo's recent paper is correct, hidden Markov models should lead to increased multivariate kurtosis if there are multiple states. So it's not the fact that you use sliding windows or not, it's the underlying data itself that would lead to changes in multivariate kurtosis. And we can't see it.
Okay, I think can I have the last question.
Well, this is on the topological data analysis. I might have misunderstood this, but what I picked up is that essentially the networks have a very, very simple topology, and you can sort of approximate the minimum spanning tree. So that's like what, n-1 edges. So does that speak to our overinterpretation of the network as a whole if we can actually cover it with much simpler means?
Yeah, okay, that's a really good question, because I spent a lot of time talking about the minimum spanning tree, those basic aspects of the topology, right? And most of that was trying to justify in the, and I'm going to say in a basic sense, the simple, unambiguous shapes in the network can be consistent across people, across scales, across parcellations, right? But that was only this zero-dimensional homology, right? Just looking at the clustering. On top of that, then we had the one-dimensional looking at simple loops, the two-dimensional looking at voids, right? And you have as many dimensions as you have network nodes, potentially, right? And so, and it's especially in the one-dimensional and two-dimensional homology that you see all the interesting detail and structure, right? So, yes, I mean, it remains to be seen properly, but broadly, as a bit of a generalization here today, I would say the zero-dimensional stuff should be almost exactly the same all the time. And if it's not, then it's like a sanity check you've stuffed up. But in the one and two-dimensional holes, or holes of degree 1 and degree 2, that's where you're going to see this incredible richness, and that's where you can pull out your quantitative features, distributed features, right, of representative holes, distributed holes, I say holes because that's just the language of homology, but yes, there's this huge detail on top of the simple structure that I was trying to find consistency in. Does that?
And we see that in human
Yes,
brain networks.
absolutely.
That's
Oh yeah, if you calculate this off a few thousand individual brain networks, you see, sometimes it's similar, sometimes it's quite different, but it's always very all I can say is sort of it's a rich playground that no one's really explored yet.
Cool. Cheers.
Okay, maybe a very quick take-home message there. If you really want to be able to compare networks, it seems that the right way to do it is with this topological approach, and the other methods are far inferior. So I'm going to try and sum up this whole thing in a couple of sentences. I mean, in some ways it's not possible. A lot of terms were used without complete definition, so that's no doubt added to some of your confusion. But let's just say two things. Firstly, use of correlation and the use of sliding windows. And as an aside, the sliding window stuff, by the way, is incredibly old methodology, first developed in econometrics in the 1930s, rediscovered on a regular basis. I could bore you to death with some names of famous techniques in other disciplines like computer vision, which are just sliding windows. The theory, though, was not developed until the 1980s in the statistics literature. Clive Loader's book on local polynomial methods is the one to read, and it's got a number of methods for automatic choice of window width. But okay, what's the take-home message? In one sense, it is, sorry, correlation's no good and neither are sliding windows. Let me, though, be more diplomatic. If you're going to use correlation methods to try to analyse brain networks, and you're going to try to use sliding window to get at some notion of dynamics, whatever that is, it's like looking at things through a badly misadjusted telescope or microscope. You're only going to see extreme versions of things. The rest of it's going to be lost in the blur. And you're going to miss out all the beautiful things in those incredible experiments that you did. And if you want to find the stuff that's really in your data, you're going to have to get somebody into your team who understands some of the different methods that were mentioned by the various speakers. So that's the story in a nutshell. I'd now like firstly to thank you all for coming, and also thank all the speakers for giving us